In this video, I'd like to take a look at Euler's method. Now, Euler's method is a way of approximating solutions to first-order differential equations. I was going to say when you can't actually solve them, but it'll do it whether you can solve them or not. Okay. So consider this example here. Suppose I've got y prime equals y squared minus t. This is not a linear equation. It is first order, but it's not linear because there's a y squared there. It's not separable. There isn't any way to get the y's and the t's together, so it's a function of y times dy times a function of t dt. It's not exact. We don't really have a way of solving this. However, we can perhaps approximate what solutions. I mean, certainly we've already looked at slope fields and seen that if you look at slope fields, you can kind of get an idea of what solution curves look like. Certainly with autonomous equations, that's what we did. And so this is the slope field with slopes drawn at all the integer lattice points. And this one here, I just made the grid a little more dense and put in at the half integers as well. And you can kind of see, I can see solutions out here that look like they're headed up, but then they really just head up fast. But over here, it looks like maybe they get caught in here and then pulled down and through there. These look like they're coming up, going back down that way. Actually, I don't know if you can see there's this parabola in here. Well, that parabola is the parabola t equals y squared. And that is when t equals y squared, this right here will be 0. So you're looking at places where the slope is 0. So they've got slope of 0 at every point on that parabola, and it looks like they're negative slopes inside the parabola and positive slopes on the outside of the parabola. So it's kind of like an equilibrium value, but it's not really, because the point of the equilibrium values was that it's a constant function and you're saying slope 0. This is not a constant function. That parabola certainly is not constant, but it is a spot where all the slopes are 0. Anyway, essentially what we want to do here is we want to approximate curves by just making these hash marks big enough to connect to each other and look at those curves. This is what I would call a linear approximation. Let's approximate linear. So here we go. We're going to be given a differential equation. This is the general setup here. First order differential equation. Y prime is some function of t and y. I'll have some initial value, t0, y0. And then I'm going to pick a step size. I'm going to approximate this. Actually, I'm lost in the slope field over here. Sorry. Hang on, let me get out of the slope field. Oh, there we go. So I'm going to start at the initial value here, and I'm going to just say, well, let's move over by so much, and then figure out what y is going to be, and then move over again and figure out what y is going to be. The thing is, I can do this because I have information about the slope. And so if I know where I am, and I know what slope I want to go at, then I should figure out at least approximately what the y value should be over there. And so this is the way I'm going to do it. Starting at t0, y0, I'm now going to calculate t1 and y1. And I do it this way. y1 is my old y value, y0, plus the slope at that point. Oh, dang, t equals x, right? That should be a t. That's better. So this is telling me the slope, and if I multiply by h, so this is like rise over run, h is the distance that I move in the t direction, so rise over run times run is the rise. So the new y value would be the old y value plus this. This is like the differential, right? We did calc 1. And then my new t value is going to be the old t value plus h. Just move over. Okay. Rinse and repeat. Do the same thing again. The second one, just take, in general, the y sub n, so the n plus, y sub n plus 1. So the n plus first point is the nth point plus the slope times h, right? Times that little change in t. And the new t value is just the old t value plus h. Okay. Let's try it with the example that we gave above here. So I'm going to make a table. So this is the differential equation. Y prime equals y squared minus t. My initial condition, I want to say, is let's start the origin. Y of 0 is 0, and use h equals 1. So here's my initial point, and here's my initial my initial t and my initial y value. I calculate the slope at that point, which happens to be 0 squared minus 0, which is 0. So then my next point, I'm going to use this to get my next point. So my next point is t is 0 plus 1. And the y value here is the old y value plus the slope times h. So there's the old y value, the slope, and h. And that still turns out to be 0. So my second point is the point 1, 0. I then use these coordinates, 1, 0, to calculate the slope at this new point, and that is negative 1, because that was y squared minus t, right? So that's negative 1. And so that slope I'm going to use to get the next y value. So the new t value is just to add on h, and then this one I'm using this 0 plus the slope, which is negative 1, times h, which is 1. And now I have a new y value minus 1. And then I'm going to use this and that to calculate to calculate the t and the y to calculate the slope, using the slope and the old y value to calculate the new y value, and so on, right? So I got 0, minus 1, minus 2. These are the y values for these t values. Let me plot those points here. So the slope was 0 initially. So I moved over 1 where the slope was 0. That got me there. This point right here had a slope of minus 1. So as I move over 1 in the t direction, it put me down here. Again, the slope was minus 1 right here, which puts me down there. At this point, the slope was, the slope was positive 1. And so that put me up to here. And then I had a slope of negative 3, which puts me down to there. And then we have a slope of, it's really big here, 11. Which would put my next one up at 7, right? And at this point, I think we're no longer looking at an actual solution to this thing, that this process has wandered off, right? And who knows what it's doing now. But maybe what we could do is decrease the step size, right? Maybe I'm just taking too big of steps to get a good idea of what's happening. But you can see this is fairly computationally intensive, and really this requires a computer. If only I had a computer. Oh, I do. Let me pull up a different way of looking at this. So, on my faculty website, you will find my live math resources. If you look up differential equations on the live math resources, one of the things is Euler's method. So this is here. I'm using live math to create this, and I'm using live math viewer here to view it. You too could download Live Math Viewer for free and view this and experiment with it. So here we go. What I've done is I've put in the differential equation, y prime equals y squared minus t. Initial conditions, h equals 1. And I'm saying, give me 100 iterations here. Here's the computations. This is the way I'm doing it. It's live math doesn't allow me to program it, but you can do recursively called functions, so I'm calling this recursively. But anyway, let's take a look at what we've got here. So here's the same picture that we just had. The grid is maybe a little more dense. You can see the points that we plotted before. Let's see, we got up to 4, 6. With t equals 6, it was supposed to be up here. Oh, there it is at 7. The next one, this is headed way uphill. This goes up really fast. So one of the things I do show here is I have calculated but hidden the first 10 points. Right? So this is calculating the first 10 iterations of Euler's method here for me. And, well, you can see things kind of go haywire. Yeah. But let's try this. Let's hide those. And let's try this with a smaller step size. So rather than a step size of 1, how about if I do a step size of, a half? Just say, let's say 0.5 here. Okay. All the calculations are the same. The first 10 points, first calculation is similar, I should say, right? First 10 points, you're getting these t values. And it doesn't seem to be wandering off as far. I think this may look a lot better. Let's take a look at the graph here. yeah, I can see this looks like it's following the curve much better. Something then goes haywire down here. But at least for a while, I'm feeling reasonably confident that that's going to be pretty good results in this range. Not out here, but in here. I could probably get better results there by taking an even smaller step size, right? Rather than a half, let's go with 0.1. You can see the first 10 calculated points. Of course, in 10 calculated points at step size 0.1, I've only made it out to t equals 1 at this point. But that's fine. Calculator, the computer's doing it. And yeah, this looks like I've probably got a pretty decent approximation of what that curve looks like. Now, I'm not finding a function, right? I'm just finding a bunch of points which would be along that line. If I wanted to know what is y when t is equal to 6, right, I could do this out until I get t equals 6, and I would have an approximate value of the function. Okay. I've never figured out what the function is, but at least I can figure out what approximate y values are. Now, there's the question of how long is this any good? How long does this stay reasonably accurate? And there's a lot that depends on the nature of the function, the nature of the function being f of t and y. What's that differential equation telling you about the slope? When you start getting really big slopes, things go crazy. There's also the matter of sort of the stable equilibrium values and the unstable equilibrium values. If you've got things where your solution curves are asymptotically approaching some other curve, then even though each approximation is wrong, that next curve that would be, you're not on the solution curve you thought you were, you're on the next solution curve, but that next solution curve is pushing you towards the same answer anyway. So if you've got some asymptotic behavior in your solutions, then this is going to work reasonably well. On the other hand, if you have divergent things, then it's probably not going to work well for very long at all. Anyway, there's some interesting things here. I find it interesting once you've got a system that'll do the calculations for you. Oh, and by the way, those of you who are taking a numerical methods class, you might use your computing skills to come up with an Euler's method formula. Anyway, yeah, I find it interesting just to look at the, to look at this slope field and see, I see curves that kind of come in. It looks like they come up and they go back down again. What if I started with an initial value over here, like of 1, -2? Will my curve, will it do what I think it does? Can it come up and then come back down again? So let's try it. So if I start at, let's hide these points. Let's start at the point 1, -2. You can see, yeah, looks like it heads up, comes over, and comes back down again. On the other hand, it looks like if I were to move over here, and let's say start at 0, -2, it looks like maybe I might even miss that parabola entirely. It might head up like this and just kind of curve and miss it. Let's see. Let's try, what did I want? No, this point over here would be -2, -2. Let's try that. Starting point at -2, -2. Right. Once you've got this set up, then you can just try different initial conditions to see what different solutions look like. Sure enough, yeah, that sort of skirts around. There's this parabola in here, and it just kind of skirts around it, heads on up to infinity. One more thing before I run out of time. You can run this backwards. So if I'm going to start, for instance, at the point 1, 1, and see what happens. 1, 1 happens to be right on that parabola. So it has a slope of 0 to start with. And you can see that initially it starts 0, and then it gets pulled down to the bottom part of the parabola. Well, I can run this backward, actually, by taking h negative. So if I take h equals -0.1 here, then it's the same starting point, but my t values are then run backwards, and you can see what the curve looks like in the other direction. Well, there you go. There's an introduction to Euler's method.